So next in this chapter, we'll see the lumped element model. When we draw a schematic of an electronic circuit, we use specific symbols to represent resistors, capacitors, inductors, diodes, and the like. In each case, the symbol represents the functionality of the device, rather than its shape, size, or other attributes. So when we draw a resistor like that, for example, in a circuit, the resistor doesn't actually look like that, or its size is not that specific size. It's just a representation to know that here is a resistor and take its functionality into consideration. A transmission line will be represented by a parallel wire configuration, figure 2.6a. So a transmission line could be represented by a parallel wire representation, regardless of its specific shape or constitutive parameters. Thus, figure 2.6a may represent a coaxial line, a two-wire line, or any other TM line. So those are some examples of TEM lines, and all of them will be represented using parallel wire configuration concept. Drawing again on our familiarity with electronic circuits, when we analyze a circuit containing a transistor, we mimic the functionality of the transistor by an equivalent circuit composed of sources, resistors, and capacitors. So, to be able to work with a transistor, we model, instead of just leaving it in some way in the circuit, we could model it in some other way to be able to deal with it and know what's composed of or its equivalence in some way. We apply the same approach to the transmission line by orienting the line along the z direction, subdividing it into differential sections, each of length delta z. So here, we'll take our parallel wire representation and divide it into very small sections, each of length delta z. And then representing each section by an equivalent circuit as illustrated in figure 2.6c. So we will take each section of those and represent it in some circuit way, we'll see. This representation, often called the lumped element circuit model, consists of 4 basic elements with values that henceforth will be called transmission line parameters. So we'll present it using 4 elements. That will be enough to be able to represent it and use it and see what it does or its effect. So the 4 elements are R dash, which is the combined resistance of both conductors per unit length. So R takes into consideration the resistance of both conductors. L dash, the combined inductance of both conductors per unit length. So L also takes into consideration the combined inductance, the conductance of the insulation medium between the two conductors per unit length. So G dash is concerned with the insulating material between them, and the capacitance of the two conductors per unit length. So we have 3 things that are concerned with the two conductors themselves, and G that's concerned with the material between them. R, L, and C are concerned with the two conductors, and G is concerned with the material between them. Whereas the 4 line parameters are characterized by different formulas for different types of transmission lines. The equivalent model represented by 2.6c, this model, is equally applicable to all TEM transmission lines. So this model is enough for this chapter, as we will deal with TEM transmission lines only. So it's telling us here that those dashes are as a reminder that the line parameters are differential quantities whose units are per unit length. So instead of taking the resistance of the whole transmission line as a whole, we divide it into small sections. Each section has the 4 elements representing it. So here all of them are per unit length and differential elements for very small sections. Expressions for the line parameters R, L, G, C prime are given in table 2.1 for the 3 types of TEM transmission lines diagrammed in part A through C of figure 2.4. So this table has those elements for the first 3 things in this figure. The coaxial, the 2-wire, and the parallel plate. It is just an example. For each of these lines, the expressions are functions of 2 sets of parameters. The first one is the geometric parameters defining the cross-sectional dimensions of the given line. And the second thing is the electromagnetic constitutive parameters of the conducting and insulating materials. So Taking a quick look, it takes into consideration two things. The geometric thing is B and A or whatever, we'll see like in 1 second. And the electromagnetic parameters, for example here, it's mu. So the relevant geometric parameters are, for example, for the coaxial line, it's the outer radius and the inner radius. So here it's a function of the inner and the outer radius A and B. This is the geometric parameters for the coaxial line. And for the two-wired line, the function is a function of d small and d capital, which is the diameter of each wire and the spacing between wire centers. So it's a function of this one, the diameter, and d capital is the spacing, so between their centers. And for the third thing, the geometric parameters are its width and thickness of the insulation. So it's this width and the thickness of the insulation material between the two plates. So you can take a look on this table. The relevant constitutive parameters, the electromagnetic ones, apply to all three lines and consists of two groups. UC and sigma C are the magnetic permeability and electrical conductivity of the conductors themselves, and permittivity, mu, and sigma are the electrical permittivity, magnetic permeability, and electrical conductivity of the insulation material between them. So it's divided into two parts. One concerned with the material between them, and the other one is concerned with the conductor itself. Appendix B contains tabulated values for these constitutive parameters for various materials. For the purpose of the present chapter, we need not concern ourselves with the derivatives leading to the expressions in table 2.1. So for now, we'll just look at this table as it is like that. We're not concerned with how it got derivated for now. The techniques necessary for computing R, L, G, and C prime for the general case of an arbitrary two-conductor configuration are presented in later chapters. The lumped element model shown in 2.6c. So this model reflects the physical phenomena associated with the currents and voltages on any TEM transmission line. It consists of two in-series elements, R and L prime, and two shunt elements, G and C prime. To explain the lumped element model, consider a small section of a coaxial line. So the first example is a coaxial line, and we'll see how it applies to it. Seen in this figure 2.7, the line consists of inner and outer conductors of radii A and B, separated by material with permittivity E, permeability mu, and conductivity sigma. So this material has those parameters, and it has a radius A and outer radius B. The two metal conductors are made of a material with conductivity sigma C and permeability mu C. When a voltage source is connected across the terminals connected to the two conductors at the sending end of the line, so as we saw previously, there is a sending end and a receiving end, and there is transmission line between them. This one has the source and this one has the load. Current flows through the conductors, primarily along the outer surface of the inner conductor and the inner surface of the outer conductor. So here current flows on the outer surface of this one and the inner surface of this one. The line resistance R prime accounts for the combined resistance per unit length of the inner and outer conductors. The expression for R prime is derived in chapter 7 and is given by this equation. So as we said earlier, we're not concerned with the derivations. This is the equation for it, and we may see the derivations in later chapters, where RS represents the surface resistance of the conductors is given by this equation. So RS here is given by this equation. The surface resistance depends not only on the material properties of the conductors, but also on the frequency of the wave traveling on the line. So as we can see here, it's a function of frequency. For a perfect conductor with sigma C equals infinity, or a high conductivity material such that F times mu C over sigma C is way less than 1, so that means sigma C is very big compared to those. RS approaches 0, and so does R prime. So if this thing is way less than 1, it means it approaches 0, and also this one depends on RS, which approaches 0, so R prime also approaches 0. So it's basically saying a perfect conductor has a very, very low resistance. Now it's saying a perfect conductor has almost zero resistance, and a conductor with high conductivity has a very, very low resistance. Next, let's examine the line inductance. which accounts for the joint inductance of both conductors. So each of R, L, and C prime take into consideration the two conductors, not just one conductor by itself. Application of Ampere's law in chapter 5 to the definition of inductance leads to the following expression for the inductance per unit length of a coaxial line. The line conductance, G prime, accounts for the current flow between the outer and inner conductors. So as we said that G prime is concerned with the material between them, here it takes into consideration the current flow, or accounts for the current flow between the inner and outer conductor. So it's saying that line conductance accounts for the current flow between the outer and inner conductors made possible by the conductivity of the insulator. It's precisely because the current flow is from one conductor to the other that G prime appears as a shunt element in the lumped element model. For the coaxial line, the conductance per unit length is given by this equation. If the material separating the inner and outer conductors is a perfect dielectric with sigma equals 0, then G prime equals 0. The last line parameter on our list is the line capacitance when equal and opposite charges are placed on any two non-conducting conductors. For example, if we have those two plates, a voltage difference develops between them. Capacitance is defined as the ratio of the charge to the voltage difference. For the coaxial line, the capacitance per unit length is given by this equation. All TEM transmission lines share the following useful relations. L prime C prime is just mu times the permittivity, and G prime over C prime is the sigma over the permittivity. If the insulating medium between the conductors is air, the transmission line is called an air line, coaxial air line, or two-wire air line. For an air line, the permittivity is E node, which has this value in farads per meter, and the permeability is mu node, which has these values henries per meter. So for air, the sigma is the electrical conductivity, actually this one is very small, on the orders of maybe 10 power negative 13. So here it considers it to be 0, and G depends on that, so G prime is also 0. So this is the end of this section. Those are some concept questions we knew from the first and the second section. Next is transmission line equations.